Do you think for the neocortex in general, do you think there's a lot of innovation to be done on the machine side? You know, you use the computer as a metaphor quite a bit. Is there different types of computer that would help us build
I mean, what are the
intelligent
physical
systems?
manifestations of intelligent machines?
Yeah, or is it?
Oh no, it's going to be totally crazy. We have no idea how this is going to look out yet. You can already see this. Today, of course, we model these things on traditional computers, and now GPUs are really popular with neural networks and so on. But there are companies coming up with fundamentally new physical substrates that are just really cool.
Mm-hmm.
I don't know if they're going to work or not, but I think there'll be decades of innovation here.
Yeah,
totally.
Do you think the final thing will be messy like our biology is messy, or do you think it's the old bird versus airplane question, or do you think we could just build airplanes
Yeah.
that fly way better than birds in the same way we can build electrical neocortex?
Yeah. Can I riff on the bird thing a bit? Because I think it's interesting. People really misunderstand this. The Wright brothers, the problem they were trying to solve was controlled flight, how to turn an airplane, not how to propel an airplane. They weren't worried about that.
Interesting, yeah.
They already had, at that time, there was already wing shapes, which they had from studying birds. There was already gliders that carry people. The problem was if you put a rudder on the back of a glider and you turn it, the plane falls out of the sky. So the problem was, how do you control flight? And they studied birds, and they actually had birds in captivity. They watched birds in wind tunnels. They observed them in the wild, and they discovered the secret was the birds twist their wings when they turn. And so that's what they did on the Wright brothers flyer. They had these sticks that you would twist the wing, and that was their innovation, not the propeller. And today, airplanes still twist their wings. We don't twist the entire wing. We just twist the tail end of it, the flaps, which is the same thing. So today's airplanes fly on the same principles as birds, which is observed by, so everyone get that analogy wrong. But let's step back from that, right? Once you understand the principles of flight, you can choose how to implement them.
Yeah.
No one's going to use bones and feathers and muscles, but they do have wings, and we don't flap them. We have propellers. So when we have the principles of computation that goes into modeling the world in a brain, we understand those principles very clearly. We have choices on how to implement them, and some of them will be biological-like, and some won't. And but I do think there's going to be a huge amount of innovation here. Just think about the innovation in the computers. They had to invent the transistor. They invented the silicon chip. They had to invent, then this software. I mean, gazillions of things they had to do. Memory systems. It's going to be similar.
Well, it's interesting that the deep learning, the effectiveness of deep learning for specific tasks is driving a lot of innovation in the hardware, which may have effects for actually allowing us to discover intelligent systems that operate very differently, or at least much bigger than deep learning.
Yeah, interesting.
So ultimately, it's good to have an application that's making our life better now, because the capitalist process, if you can make money, that works. I mean, the other way, Neil deGrasse Tyson writes about this, is the other way we fund science, of course, is through military, conquests. So
here's an interesting thing we're doing on this regard. So we've decided we used to have a series of these biological principles, and we can see how to build these intelligent machines. But we've decided to apply some of these principles to today's machine learning techniques. So we didn't talk about this principle. One is sparsity in the brain. Most of the neurons are inactive at any point in time. It's sparse, and the connectivity is sparse, and that's different than deep learning networks. So we've already shown that we can speed up existing deep learning networks anywhere from 10 to a factor of 100. I mean, literally 100, and make them more robust at the same time. So this is commercially very, very valuable. And so, if we can prove this actually in the largest systems that are commercially applied today, there's a big commercial desire to do this. Well, sparsity is something that doesn't run really well on existing hardware. It doesn't really run really well on GPUs and on CPUs. And so that would be a way of sort of bringing more brain principles into the existing system on a commercially valuable basis. Another thing we can do is we're going to use these dendrites. models of I talked earlier about the prediction occurring inside a neuron. That basic property can be applied to existing neural networks and allow them to learn continuously, which is something they don't do today. And so they solve
the dendritic spikes that you were talking about.
Yeah. Well, we wouldn't model them as spikes, but the idea that you have that today's neural networks have something called a point neuron, which is a very simple model of a neuron. And by adding dendrites to them at just one more level of complexity that's in biological systems, you can solve problems in continuous learning and rapid learning. So we're trying to bring the existing field, and we'll see if we can do it. We're trying to bring the existing field of machine learning commercially along with us. You brought up this idea of paying for it commercially along with us as we move towards the ultimate goal of a true AI system.
Even small innovations on neural networks are really, really exciting.
Yeah.
Because it seems like such a trivial model of the brain and applying different insights that just even, like you said, continuous learning or making it more asynchronous or maybe making more dynamic or like incentivizing.
Or
making
more
it
robust, even just more robust.
And making it somehow much better, incentivizing sparsity somehow.
Yeah. Well, if you can make things 100 times faster, then there's plenty of incentive there.
That's true.
People are spending millions of dollars, just training some of these networks now, these transformer networks.